So first we will see what a transformer is. I won't really go into much details of transformer. Transformer is fundamentally two blocks, encoder and decoder block. Encoder which will take the sequence of tokens as input. Actually sequence of tokens are converted into word embeddings. Word embedding will be a vector corresponding to each token, and the encoder produces another set of word embeddings as output, and it will be fed back to the decoder. So decoder operates in a stage by stage manner. The first decoder D1 will actually take the output of the encoder plus a BOS tag, beginning of sentence tag, as input, and it will produce output T1. T1 will be fed to T2. T1 will be given as a input to the second decoder, and you will get the output T2. T2 will be fed as input to the third decoder, and so forth. So for each decoding block, the output of the encoder is also given as the input, and there is something called cross encoder decoder attention mechanism, which is the whole fundamental building block of the decoder. And I don't really go into the details of the cross encoder decoder attention mechanism. That is actually very popular mechanism, which actually makes this concept of decoder work in the first place. So what you need to know here is that the input of the decoder is coming in stages. Means first input you give, and you will get output from the decoder, and that output will be fed as input to the second decoder. So this works in an auto-regressive manner. Okay, in training you are giving the first input to the first decoder, and you will get some output. That output may not be really optimal output, so but it doesn't really matter. You will be feeding that same output as the input to the second decoder, and you will get the it goes on like that, and you will get the final output. Now when you're training the system, what happens is that let's say T1 has given us input to the first decoder, and it produces output some D1. Now the problem is D1 may not be the accurate output. It is just a predicted output. Now there will be an accurate output or the ground truth output. So you have a mechanism to get a loss function, right? So this loss will be fed back in the backpropagation stage, and the parameters of this parameters of the decoder will be updated. So this is how the training goes. So fundamentally, transformer is a probability distribution of target given input I, parameters by two set of parameters theta e and theta d. So the encoder basically is a function which actually takes input a sequence of word embeddings and convert it into a sequence of another word embeddings. Decoder is fundamentally a conditional distribution of a set of target tokens given a set of output tokens from the encoder, which can be represented as a P of Ti given Ti minus 1 and O. O is the whole output of the encoder. So from this you can see that the autoregressive nature of the decoder, P of Ti given P of Ti minus 1. So if there is no Ti minus 1, you cannot get the Ti minus. If there is no Ti minus 1, you cannot really get the Ti. So it operates in a time stages. It operates in time stages. So now we will see this proper generative pretraining. So given a sequence of words W1 is equal to W1 up to Wn, maximize the probability of observing one particular word given all the previous words. P of Wi given W1 up to W2 up to Wi minus 1 for all I. This is what we want to actually maximize, and we are given a sequence of words. So they are using the decoder part of the transformer for this purpose. And when immediately we think about decoder, what comes into our mind is the series of decoders. The output of first decoder is fed as the input to the second decoder, The output of the second decoder is fed as the input of the third decoder. This is how generally when we think about decoder in term, with respect to the machine translation or question answering stuff. But the point about this paper is that they are just using only one particular decoder, and they have not really clearly explained like how a P of Wi given W1 and W2 up to Wi minus 1 maps to a decoder. But I think this is how they will be mapping. For example, take the case of this particular expression, P of good given I am doing. Okay, what is the probability of observing the word good given the previous words I am doing? So this gets mapped to a decoder in the format shown in this figure. Doing is the present input. In your self-attention stack, you have two words I and am, or the input still at till this point, and you're expecting a output good. Now once we are running this particular block of decoder, you probably might get some other output, like maybe better or bad or something like that, and you know what you are expecting. You are expecting a word good, so you have some kind of loss measure. You can feedback, you can actually give that particular loss back to the backward question algorithm, and you can train the parameter vector theta in this case, to output good next time when we are giving the input I am doing. So this is how I think they are doing it. But they have actually referenced another paper. um, they have cited one paper titled Generating Wikipedia by Summarizing Long Sequences. But in that paper, what they are doing is that they are actually using a decoder in an autoregressive manner. They are just not using one decoder, they are using a series of decoders in an autoregressive manner. And the authors of this particular paper are saying that they are just using that particular decoder architecture, but in the paper what they have only given information about one particular decoder. It's slightly confusing. So look at this particular expression, P of Wi given W1 up to Wi minus 1. This can be represented using a transformer in this particular format. um, your Wi minus 1 is going as input to the transformer decoder, and the input till the point Wi minus 2 is present in the self-attention stack inside the decoder, and the decoder performs this self-attention operation on this present input Wi minus 1 along with the W1 and W2 up to Wi minus 2, whatever is present in the self-attention stack till this point, input till this point, and it expects an output Wi. This can be drawn in a slightly different format. There is no sort of differentiation between the input and the whatever is present in the self-attention stack. Everything is input now. W1 up to Wi minus 1 is going to go as the input, but that index of I is present. Okay, that information that it is the input till this particular point is present. It cannot really look ahead, and so there is something called a forward mask which prohibits the decoder from looking ahead. It can only look till this present index I minus 1 in this case. So this is actually interchangeably we can actually use this representation, but for the purpose of this particular video we will use the first expression so that we understand that we can actually relate it with your original decoder of the transformer. But this is mostly similar. Means all we are saying is that in the decoder you have access to the input till I minus 1, and you are expecting the word Wi. Okay, that's all we are saying. You have the access to the inputs till the point I minus 1, and you are expecting the word at ith index as the output, Wi as the output. Now we are just expanding this optimization objective. Putting a log, so the sum will come out, log will go in. So it's a sum of a log of a probability of one particular word given all the previous words. Not that this each and one of the terms in this expression can be represented by one particular decoder itself. Okay, so when you are optimizing, there is no sort of order or anything like that. Okay, you can actually optimize it in a whatever order you want, because see W1, when you set log of P of W2 given W1, this W1 is not really coming from anywhere. W1 is, you know the sequence of words, you know what word W1 is. So you are directly giving W1 as input, and you are expecting W2 as the output. And if the W2 is not what this decoder is producing as output, you can actually feedback whatever is expected, whatever is the loss measure coming from the expected value, and you can actually train the parameters of this particular decoder, so that when next time when it is given W1, then you will get a W2 as the output. Um, so the point here is that each and one of these blocks are independent. You can actually train it parallelly. Sorry, you cannot really train it parallelly. That is a wrong assumption. You cannot really train it parallelly, because if you are assuming that there is only one decoder, so you cannot really train it parallelly. You can train it independently. Okay, W2 is not really going as input to it. This is not a series of decoders. This is just one decoder only. Okay, this in this drawing it is just showing the different instances of one same decoder only. It is not that W2 is just going as the input, or it's not that W2 is connected as, it's not a series of decoders where W2 is connected as the input to the decoder 3. That's not the case here. So you know the sequence of words, you can actually train for each instance of wi given w1 up to wi minus 1, you can actually train independently, so that for this sequence of words, the w1 up to w1 up to wn, for this particular sequence of words, the probability of observing wi given w1 up to wi minus 1 for all I will be maximum, so that this expression of yeah, so that this original language modeling objective would be maximized.